Hello and welcome back to the GeoPy Advanced Workshop Part 2. In this section we are going to be diving into loops, automatic material optimization and plot generation. First of all, I would like you to go back to GeoDict. Go to Macro, Execute Macro Script and unfold the project folder if necessary. Select workshop3.py, the last file we worked on, and click Edit down there. Then the editor should come up again. Now please first save the file. So go to File, Save As, and store it as workshop4.py. Now we go all the way down. Probably this function is unfolded now for you, so let's just fold it again. Click the minus in front of def. Let's remember what we did last time. We wrote this function which generates a grain structure with a given solid volume percentage, as well as adding some binder with a given solid volume percentage too. Running a flow simulation, grabbing the permeability value from that result and returns it. Then we added a line which calls this function with the fixed values of 25 and 15, so a total SVP of 30%, and shows the resulting probability per value. What we want to do now is loop over a certain range of values for SVP and binder and call the function for each SVP value and display the corresponding result. To do this, we introduce a for loop. Please go to a line just above the perm assignment and write for SVP in range brackets 20, 50, 5. Now what this does is it varies the SVP value in a range from 20 to 50 with a stepping of 5. And so it starts at value 20, increments that by 5. So it is 20, 25, 30, up to, but not including, the 50. Return and add a new line for the binder, writing for add binder in range 0, 25. Now what this does is it varies the add binder value in a range from 0 to 15 with a step of 5, excluding the stopping value of 20. Please intend this line such that this for loop is part of the body of the first loop. That is what these loops are doing, and we take the rest of the code and we indent it twice again. So that is actually executed in the body of the second loop. Within the body, we have an SVP value which varies from 5 to 45 inclusively, as well as an add binder value which varies from 0 to 15 inclusively. We replace the function values with our new variables SVP and add binder. For each iteration of this for loop with a different SVP and add binder value, our function is called. The corresponding permeability is obtained, and that permeability is then displayed on the screen. Now, to make this a bit nicer and to actually know to which SVP and add binder permeability that we are seeing correspond to, include a new variable inside the message box string. Replace the previous element with f, the permeability for an SVP of curly brackets SVP, and added binder of curly bracket add binder is curly bracket perm. We've seen this construct before. This is a format string because it's introduced by an f, which means nothing but that Python will go and replace these parts of the string which have curly brackets by the corresponding variable values. We will get sentences like the permeability of a SVP of 25 and added binder of 5 is some number. And this is what is going to be displayed. So after each run, we'll know the corresponding pair of solid volume percentage and permeability. Now let's save the file by pressing Ctrl S and go back to GeoDict to try it out. If necessary, open the macro execution dialog again by going to Macro Execute Macro Script, unfold the project folder, possibly hit refresh until you see workshop4.py, select it and click Run. Anytime when you are prompted to overwrite, just click Overwrite. Now we see the first result, so it says the permeability for a SVP of 20 and added binder of 0 is 1.6159 to the power minus 10. Now if we press OK, it will do the next run, and we are getting the next result, probability for a SVP of 20 and added binder of 5, etc., etc. It should probably run more smoothly for you because I had some intermediate result here, which it asked me to overwrite a few more times, but you will get a message box for each intermediate result. Now we basically have created a very simple parameter study. As many of you might know, we could also have done this by using a very macro function list. By introducing SVP and binder as variables of the macro, we could have used the vary functionality and we could have entered a range of number for which to run the macro and would do the same thing basically. But what the vary macro cannot do is, for example, aggregate these results, and one form of aggregation is to plot the results, and this is what we are going to do next. Please go back to the editor, so possibly go into Execute Macro, choose Workshop 4.py and click Edit, or just go back to Notepad++ if it's still open. So save it as Workshop 5.py. Now we're going to go and plot the permeabilities against the solid volume percentages of grain GeoCreate and add binder. For this, please for now just delete the parts beyond the function, delete the for loops. Then we're going to do import matplotlib.pyplot as plt and import matplotlib.colors as colors. Matplotlib is the most famous Python plotting library and probably the most famous plotting library overall, and you can find many tutorials and lots of documentation of it online if you want to change the plot, for example. To have something to plot, we'll need to fill a table of values first. So we'll start by doing SVP values equals list of range 5,50,5 and binder values equals list range 0,20,5. We take these ranges of SVP values and binder values. So that is 5, 10, 15, etc. up to 45 again, as well as 0, 5, etc. up to 15 again. Turn it into lists and store them in a variable each. We do this actually because we need this in two places, as you can see, so we'll just write it once. We don't want to repeat this. We also define a list of permeability values, but this list is initially empty, so equals bracket. So I have two lists of values as well as one initially empty list. But we are going to compute the permeability for each SVP value and each binder value. Then we are going to append it to this perm values list. So after that, we're going to have two lists of values, and we are going to have a two-dimensional list of permeability values which correspond to the combination of the previous two. Again, we do a for loop for SVP in SVP values. So actually, now this for loop executes the same values that we had earlier, because this is just a list of the same SVP values as before. As we need the list of permeabilities to be two-dimensional, we introduce an intermediate empty result list. Result equals empty brackets. Again, we do the inner for loop. Intent for binder in binder values. So actually, this for loop now executes the same values that we had earlier, because this is just a list of the same binder values as before. Now again, this is actually the same line as before. So perm equals create structure and run simulation, SVP and binder. So run the simulation for that SVP and binder combination and obtain the permeability. And then we do result append perm. Note that you have to reuse the right indentation for it actually be inside the inner for loop. This loop will again execute for each SVP and binder value, obtain the permeability, take it and append it to this list of perm values, which is empty at the beginning of the inner loop, but in the end will be filled. Now we go back in the indentation by one level. We have stored the results from the inner loop in a temporary result list. Now we append this one-dimensional result list to our perm values list, making it two-dimensional process, thereby getting a table for our plot. Now we go back in the indentation to the front. So we start on the left-hand side again. This signifies that we are outside the for loops again. We do plt.clf round bracket. This clears the plot area if there is any plot in memory basically. As our permeability depends on two variables, the perm values list is two-dimensional. We will not plot a function here, but actually a color mesh. We add an image. So we do pld.pColorMesh, round brackets, binder values, comma, SVP values, comma, perm values. What this does is it plots SVP values and binder values on the x-axis and on the y-axis and use the color values as the perm values. Then, unfortunately, we cannot just automatically show the plot on screen. So what we are going to do is we will save the plot as a PNG file. We do plt.savefig, which stands for figure, and we go round brackets permeabilities.png. It saves the plot that we have generated here as an image as permeabilities.png. As we plot the colored image, let us adjust the color bar too. First, go a few lines back and include the suffix c equals before the line plt.pColorMesh, and use the variable to activate the color bar by including the line plt.colorbar round brackets z. Next, go a few lines back before clearing any remaining plots and extract minimal and maximal value from the matrix of permeabilities. Luckily, we know that the highest permeability will be at the lower end of the SVP spectrum and vice versa. So type z-min equals perm values of the length of SVP values -1 and the length of binder values -1. And c-max as the element of perm values at 0, 0. Use this to set the color bar to logarithmic scale between the minimal and the maximum value. Therefore, we attend plt.pColorMesh with additional attributes. Include comma norm equals colors.logNormal round brackets z-min, z-max, and to make the image more pretty, also attend comma shading equals Gouraud to plt.pColorMesh. Save the file and let's try it out. So we go back to GeoDict, macro execution, and possibly hit refresh until we see workshop5.py, select it and click run. Now it will ask again to overwrite several times. Just click overwrite. Now we should go into the project folder via Explorer. So go to the workshop folder, go to the project folder. There we should see a PNG file called permeabilities. Just double click it to open it, and we can see an image which plots the SVP and the binder versus the corresponding permeabilities with logarithmic imaging here. Of course, you can make this plot nicer, but this would be kind of outside of the scope of this tutorial. But you can find, as I said, many matplotlib examples online. So for example, to manually set the scale of the axis, give it a title, or give an axis title for the x and y axis, or even print the image in 3D. Now let's assume you have a good GeoDict model of a material with a free parameter. For example, you have a grain structure with binder and the solid volume percentage as a variable. Now your goal is to find a material within that parameter space which has the desired target permeability. For this purpose, we can do a simple automatic material optimization, and I will show you how. Again, open workshop5.py and save it as file save as workshop6.py. Now we'll go and remove all the code below the function. We'll begin as follows. Say you have a given target permeability. Here we will give a fixed permeability, but of course you could also make this a macro variable so that the user can give a target permeability from outside. Let's say 10 to the power minus 12. We need an error function first. This error function receives a list of variables. So def error function of x. Here the list x will be our SVP value and our binder value. The error function executes our function which generates a grain structure with a given solid volume percentage, as well as adding some binder with a given solid volume percentage, runs a flow simulation, grabs the permeability value from that result and returns it. Thus, use perm equals create structure and run simulations, round brackets, and add the values of our parameter list, x of 0 and comma x of 1, round brackets closed. Then we use our target permeability. Target perm equals 10 to the power minus 12, and return the absolute relative error between those two values. So we have return abs of perm minus target perm divided by target perm. This error function maps the parameters to be optimized in an automatic optimization to a scalar error value. For an automatic optimization, a first guess for our variable is necessary. Therefore, we include initial SVP equals 35 and initial binder equals 10, as well as mapping them to the initial list of variables. x0 equals initial SVP, initial binder. So now for our automatic optimization, we import another standard Python library, namely SciPy, as follows. From scipy.optimize, import minimize. SciPy.optimize provides functions for minimizing or maximizing objective functions, here chosen to be the simplex algorithm nelder-meet. We call this optimizer simply by writing res equals minimize round bracket start of error function x0 and then adding some details about the method used. So method equals nelder-meet, and adding abortion criteria for the optimization iteration. Here parameter and error function tolerances within the final simplex. So options equal brackets xtol to be 1 to the power minus 2 and fatol as 1 to the power minus 3. The optimization runs until the required tolerances are achieved. The result is stored in a dictionary, here called res. We extract the information required for us. Solution equal res of x. This extracts the optimized parameters, aka grain SVP and added binder SVP. And perm equal res of fun function. extracts the latest error function evaluation corresponding to the parameters in the solution. The SVP and binder values that it has after the last iteration of the optimization can be inserted into a final message box, as you can enter new lines in this message by writing \n permeability curly brackets perm. We include an output which has 3 lines in a box, with the final SVP value, the final binder value, and the final permeability after this optimization process. So we have the new line gd.messageBox f-string final SVP curly brackets with solution 0 \n final binder curly brackets with solution 1 \n permeability error curly brackets 100 times perm and \n. Let's save this file. Now we can go to GeoDict and try it out. Again, if necessary, hit refresh in the macro execution dialog until you see workshop6.py and then click run. What this optimization has done is a simplex algorithm. In each iteration step, and with 2 variables to vary, we have a triangle spanned. The vertex with the largest error value is then moved in the direction of the line given by the other 2 vertices. Of course, this is an oversimplification, because this is assuming that the correlation between the SVP and the permeability is strictly monotonous, and it ignores the random, the stochastic nature of the structure generation in this case. But it is a simple approach that can sometimes work, and it is definitely a good introduction for what you can do with automatic optimization and how easy it is to use. This loop will then run for a couple of times, and in each step it will evaluate up to 2 parameter pairs. If it asks you to override, just click override, please. Now we get an output with a final SVP of 20.772%, binder added with 10.876%, and the corresponding relative permeability error of 0.507%, which is relatively close to our target probability. We can see what it did when we go to the Explorer. So go to our project folder and we can see that it tried all kinds of probabilities here. You can see it in the grain geo names that it has narrowed down towards the target range. Again, as I mentioned, this is a very simplistic approach. But in case you have really monotonous behavior between the input and the output variable, this can save you a lot of time in getting a structure with properties close to your target properties, because otherwise you would probably do a grid search as we did earlier. But this is a much more intelligent approach. There's such a monotonous behavior and it gets you much closer to the target values with less steps possible. And as you've seen, it's quite easy to be used. After completing the automatic optimization of our structure generation parameters, we'll probably like to illustrate our results too. Similar to the results of our parameter study, we want to automatically store a result image. Please go back to the editor. So possibly go to Execute Macro, choose workshop6.py and click Edit, or just go back to Notepad++ if it's still open. So save it as a new and our last file, workshop7.py, and now we're going to go and plot the resulting structure with GeoDict itself. For this, use the session macro recording to copy image storing to your script. Click the Save Image As button in the GeoDict menu, select Crop All Empty Space, and click OK. After selecting a file name and saving the image, you will find two new entries in the session macro list. Now select them, Ctrl-click both, and use Copy to Clipboard to store these in buffer. Paste this buffer in your script, preferably next to the other functions and prior to the main part. Then encapsulate the parameter dictionaries and command execution into a function and replace the file name with a variable for this function. So the newly recorded dictionaries and commands are hidden beneath the function. Def save image of file name. Indent the function body so that Python knows where the function ends. We can now call this function at the end of our script to store the final image in our project folder. So type save image of example.png. Note that the visualization settings are not set here. The image will be made with your current point of view. Of course, the visualization setting can be scripted in the same way too, but this would blow the context of this workshop. Save the file and let's try it out. So we go back to GeoDict, macro execution, and possibly hit refresh until we see workshop7.py. Select it and click Run. Now it will ask again to override several times. Just click Override here. Now we should go into the project folder via Explorer. So go to the workshop folder, go to the project folder. There we should see a PNG file called example. Just double click it to open it, and we can see an image which shows the GeoDict extraction of the last structure generated. This way of generating images from GeoDict is quite important for our next part, enabling automatic report image generation within our scripted workflows. So this concludes the second part of our GeoPy Advanced workshop. You have learned how you perform parameter optimizations, included different imaging styles, started a SciPy optimization routine, and recorded a GeoDict macro to visualize the digital material. In the third part, we're going to be talking about how you can create custom PowerPoint reports from your simulation results. Now there's again a 15-minute break. You can ask questions if you want in the chat or even orally. We are going to be seeing each other then after this break.